Okay, here are the sample problems for class 23 of Math 117. This first rather minor calculation, when put together with the second set of workshop problems, will give us a complete verification that if you plug the Black-Scholes formula for the fair market value of a call option into the Black-Scholes partial differential equation, it works. And what I need to do is to compute the derivative of the quantity that appears in the first of the two terms into which I split the Black-Scholes equation. If you look at the middle line in the statement of the problem, this u of t and x is the fair price of an option after time little t, which has to be smaller than capital T, has elapsed, given that the fair market price at that time is x. And when we differentiate that, we're going to get derivatives that involve n prime. So I want to compute n prime of g. N prime, since it involves integrating the density function for the normal distribution, has a square root of 1 over 2 pi in it. I will multiply by the square root of 2 pi so that in the explicit expression that doesn't show up. All that survives in the explicit expression is the exponent of minus. Now we've got g of t and x, but I'm going to write g of t and x as the sum of h of t and x and sigma times the square root of capital T times little t. Now I'm going to expand that square and the exponent to get three terms. The first term I want to write separately. That's e to the minus h of t and x squared over 2. The other two terms I will combine, so I will be multiplying that by the product of the cross term, which is minus sigma times the square root of t minus little t times h of t and x. And then the last term results from squaring the sigma times the square root of t minus t. There it is, and that's got a factor of 1/2 on it. Now I'm going to plug in h of t and x, but I'm going to exploit the fact that h is equal to g plus sigma times the square root of capital T times little t. So what have I got? I've got minus sigma in the exponent. I'm just working on the exponent here, times the square root of big T minus little t times g of t and x, plus, because h is g plus sigma times the square root of t minus t, and I'm multiplying by another factor of that. That combines in a nice, neat looking way, and then I've got to subtract off 1/2 of that. Okay, look at the formula for g. That's got a sigma times the square root of t minus t in the denominator. Conveniently, we are multiplying by that. So all I get is what's left in the numerator, the log of x over k plus r plus sigma squared over 2 times capital T minus little t. And then I have left over from the previous line two terms that partially cancel, leaving plus 1/2 sigma squared times capital T minus little t. And how convenient, if I get the signs right. I see what was wrong. I forgot that minus sign. And that should be a minus sign. That's nice because now I've got minus sigma squared over 2 times this, canceling plus sigma squared over 2. I'll get rid of the explicit minus sign on the first term by flipping over the logarithm. And what's left on the second term is just r times capital T minus little t. So, what have we concluded? The square root of 2 pi times n prime of g is equal to the product of two terms, e to the minus h over 2, and then what's left beyond that is the exponential of this exponent that I just calculated. So I'm exponentiating a logarithm and getting k over x, and I've got the exponential of minus r times big T minus little t. Okay, I'll divide both sides through by 2 pi, and I will multiply both sides through by x. So I get x n prime of g of t, and x is equal to, well, there you see, staring at you, the normal density function, the derivative of the function capital N for h of t and x. We multiplied through by x. That gets rid of the x in the denominator, leaving just the k, e to the minus r times capital T minus little t, and we are done. There's nothing of particular mathematical or economic interest in this. It's just that without this calculation, which is rather a pain to figure out how to do, we can't complete the proof that the Black-Scholes formula satisfies its eponymous differential equation. This second problem is an attempt to show you why the Black-Scholes partial differential equation might actually be useful for some small calculations. So let's write this down. What it says is the interest rate times the value after time little t has elapsed, and the price of the underlying security at the time is S, can be expressed as the sum of three terms. The first one is v sub 1. That means the partial derivative with respect to its first argument of the price of the option, the rate at which the option is increasing in value, assuming that the price of the underlying share stays the same, plus another term where you multiply by the interest rate and you multiply by the share price, and then you multiply by the derivative with respect to the price of the underlying security. I don't have the economic visualization power to see why that should be in there. And the last one is even more mysterious. It involves the square of the volatility times the square of the price of the underlying security times the second derivative of the price of the option with respect to the underlying stock. This quantity will be non-zero if things change at a different rate when the price of the underlying share goes up than they do when it goes down. And the reason this can be useful is these four quantities are related. That means if there's one of the four you don't know, and you know the other three, you can make a prediction. So let's try this in a concrete example. Price is equal to 10. Volatility is equal to 0.2. The interest rate is 0.05. The strike price for the option is 12. And the total time to maturity is 4 years. And since we have the Black-Scholes formula, we can get numerical estimates not only of the value of the option, but of all its partial derivatives, and then we can plug them into the equation to see how well this equation is satisfied when you estimate these derivatives with finite differences. I'm going to do this using a time increment of 1/10 of a year and an increment in share price of $1. And a word about estimating a second derivative. The way you estimate the second derivative of a function x is you take the average when you increase x and decrease x both by the same amount, and then you subtract from that twice the current value of x and divide by the square of the increment. Okay, I'm not going to do this calculation by hand. I'm going to have R help me out. So I have fired up RStudio, loaded the file blackscholes.r, and here goes. The first number that we want is the option price when the first argument, that is the share price, is 10, strike price of 12, 4 years to maturity, everything else is the same. And the first time I do this evaluation is for the case where I just realized it does help to define a function before you call it. So let's define this function v. The function that I'm calling v is just the Black-Scholes function evaluated when the time is capital T minus the last argument, little t. So this will let us evaluate the option value as a function of time. V subscript 1 is an estimate of the partial derivative with respect to the first argument, and there's a final argument to this one that lets me decide what increment I want to use. If I make the increment too large, I won't get a good approximation to the derivative because the changes are too large. If I make it too small, I might be done in by round-off errors. Similar one, V2, gives me partial derivative with respect to the second argument, and the last one gives me two partial derivatives with respect to the second argument. Okay, now we can get the numbers we need. So the first one is the value when t equals 0. The second one is the option value a little bit later when t is equal to 0.1. And you can see by looking at the numbers at the bottom that in that case the option value goes down as a function of time. It's also useful to evaluate the option at time t equals 0 for both a larger value, 11 for the underlying share, and a lower price, 9 for the underlying share. If I want to do V1 the hard way, all I have to do is to subtract the first quantity I calculated from the second one. I have a built-in function that does the job, and it gives exactly the same value. Similarly, by using the option value for an underlying price of 11, subtracting off the option value for an underlying price of 9, and dividing by 2, I can get an estimate of the partial derivative with respect to the price of the underlying share. But I've also got a function that does the same thing and gives the same results. And finally, to estimate the second derivative, what I have to do is evaluate for a share price of 11, a share price of 9, and a share price of 10. Take the sum of the first two and subtract off twice the third of them, but I've got a function that does that. Let's let R know our interest rate, 0.05, our volatility, and our share price. And now I can evaluate the quantity on the left-hand side of the equation. That's the R times V. On the right-hand side of this differential equation, there are three terms. The first one just involves the partial derivative with respect to the first argument, time. The second one involves the partial derivative with respect to the underlying price. That has to be multiplied by the product of the price S and the interest rate R. And the last and most mysterious of these involves the second derivative and has to be multiplied by the square of the volatility times the share price. I can add together these three terms, compare it with the left-hand side of the equation. I get pretty good agreement, not perfect agreement because I used finite increments. If you want to play around with this on your own, I think if you use smaller increments, you get better agreement. But the point of this was simply to show you how you can get numerical estimates of these various quantities, because that will let you, in the workshop problems, reach some interesting conclusions about option pricing.